Hello, Year 8. Before we make a start on the lesson, there are two questions for you to do now. So pause the video and have a go at those. How did you get on? So question number one, you basically have to imagine a door and you apply a force to push it open. What you'll find is that it's easier to push it open if your hand is further away from the hinges, which we also call the pivot. So basically, the closer the distance of the point of application of the force to that hinge, the more force you would need to apply to push the door open. The further away you are, the less force you'll need to apply to get it to open. And the second challenge question basically says that the answer to that is if the gas temperature gets hotter, even if the volume is kept constant or the same size, then the pressure would go up because the particles move faster. And when particles travel faster, they gain more kinetic energy. So there are more collisions with the walls of the particular tube. So on to today's lesson, which is P3.7 in your Activate book, which is about turning forces. And the learning objectives are to describe what is meant by a moment and to be able to calculate the moment of a force, to describe what is meant by the law of moments, and to describe what is meant by the center of gravity. So here we have a seesaw that turns about something called a pivot, and I've marked that pivot there on the diagram. There's an apple on one end of the seesaw and a girl on the other. So the girl creates what we call a turning force, which is a certain distance away from the pivot. And this turning effect of her force is what we call a moment. This moment depends on two things. It depends on the distance from the pivot to the force, and it also depends on the size of that particular force. So in this case, the force's size is the weight of the girl. Now the apple will also have a turning force, but this will be much, much smaller than the girl's turning force or moment. There is an equation that we can use in order to calculate the moment, and that equation is given over here. So to find the moment of an object or a person, you just need to multiply the force, which is measured in newtons, by the distance from the pivot, which is usually given in centimeters or meters. Now, the unit for moments is Newton meter or Newton centimeter. And I've shown you here a formula triangle. So if the question asks you to find the force and you know the moment and you're also given the distance, you just need to cover up the force, and the formula triangle tells you that the moment divided by the distance will give you the force. If you had to find the distance from the pivot and you were given the moment and you're also given the force, you would cover up the distance and you should be left with the moment divided by the force. We have a law of moments as well, and that law states that the sum of moments in the clockwise direction is equal to the sum of the moments in the anti-clockwise direction. So here we see that we have a seesaw that is balanced and it's not moving one way or the other. That means that the seesaw is in equilibrium, and it means that the sum of the clockwise moments are equal to the sum of the anti-clockwise moments. So the girl with the yellow hair is providing the turning effect in the anti-clockwise direction, and the girl with the red hair is providing a turning effect or moment in the clockwise direction. Okay. So here we have another example where we have a seesaw And this seesaw is said to be in equilibrium because it's not moving in any direction. That means that it's not turning one way or the other, because the sum of the clockwise moment is equal to the sum of the anti-clockwise moment. So we can see here, we can actually confirm this and check what is the size of the clockwise moment and what is the size of the anti-clockwise moment. And then if they're equal to each other, then we know that the object is in equilibrium and not moving. So let's check that and do a calculation. So first of all, let's take a look at the clockwise moment. That clockwise moment or turning effect is being provided by the man sat on the right hand side, and we can calculate his moment, which is the force that he provides, which is also equal to his weight, and that's given as 1000 newtons. So we multiply 1000 newtons times the distance that he sat from the pivot, which is given as 0.5 meters. So if you multiply those two together, we get 500 Newton meters. Okay, so that's the moment in the clockwise direction. If we take a look at the anti-clockwise moment, or the turning effect that seems to be going into the following the clock in the anti-clockwise direction, we can see that that moment is equal to the force, which is provided by the girl, and that's her weight, that's 500 newtons, multiplied by the distance that she's sat away from the pivot, which is 1 meter. That gives us 500 Newton meters. So we can see very clearly, okay, that because the moments are the same and they're equal, therefore the seesaw is in equilibrium or it is balanced. So in this example, we are taking a look at an everyday situation that involves moments. So here we have a possible person about to fall back on their chair. So let's say if you're leaning back on your chair slightly, then there is a turning effect, which is caused by your weight that is acting at a point of rotation or a pivot. And the pivot in this case are the back legs of the chair. So your weight is generating a moment about this point, the back legs of the chair, and that brings you, hopefully, will bring you forward and back down onto four legs. But when you use your feet to push back, you create a moment in the opposite direction, which is about the same point of rotation. So it's again at the pivot point, which is the back legs here again. Okay, if this is balanced, then the two moments, the one caused by your feet pushing back and also the other one caused by your weight, if the two moments are balanced, then equal in size, then you won't move. But if the moment isn't balanced, then you have a good chance of falling back. There's an important term that we need to know about, which is related to this situation that we just looked at about the falling chair. It's called the center of gravity, sometimes also called the center of mass, and it's where all the weight of an object seems to actually act. It doesn't matter what object it is, any object, whether it's three-dimensional or two-dimensional, irregular shaped or regular shaped, all of the weight of that object seems to act through one particular point, and that point where all the weight seems to be acting in an object is called the center of mass or center of gravity. Okay, so if we look at this diagram, we've got three situations, and if you look at diagram B first of all, this is where we can see that the center of mass is directly above the pivot, okay, and in that case the turning forces are overall zero, so that chair will not fall forwards or backwards. If you look at picture A, the weight, which is here the center of mass of that particular person, or center of gravity, is to the left of the pivot. That will make the four legs of the chair come to the ground. If you look at picture C, we can see that the center of mass of the person is to the right hand side of the pivot, which are the back legs of the chair, and that means that that person will have a turning effect and will fall back. Okay. So this is an example of a type of question that you may get asked in an exam. Okay, so you've given this diagram which shows a person who's about to lift the end of a heavy wooden pole. Now again, remember that this is an object that has a center of mass, and the center of mass seems to be acting at one particular point where all of the weight is directed. Okay, and this looks like a regular shaped object. So for a regular shaped object, the center of mass will be at the center of that particular object, okay, at one particular point, and that seems to be given over here as 2.5 meters from the axis of rotation, which is also the pivot. Okay, so it says you need to calculate the moment produced by the weight of that particular pole. All right, so we use our moment equation, which is force times distance from the pivot, and that should give us the moment. Now the force in this case is the weight of the pole, which is acting 2.5 meters from the axis of rotation. So we do 500 newtons, the force, multiplied by the distance of that force from the pivot, which is given as 2.5 meters, and we get 1,250 Newton meters. Make sure that you write down the units as well, okay? And now hopefully with this PowerPoint you should be able to answer some of the questions for activity 2.